Page 45. In the last section of Chapter 2, we're going to look at the physical properties of metals, nonmetals, and metalloids, also called semi-metals. We're going to look at some periodic trends in the elements in terms of their size, their ionization energy, and electronegativity. We'll look at some trends in acidity and basicity of the element oxides and the element hydrides. And we'll write some balanced equations for the reaction of the element oxides in water. Take a look at the metals. On the periodic table, I've colored all the metals green. Of the 118 known elements, about 93 are metals. And I say about because some of the elements in the lower end of the 7th period are very short-lived, half-lives, fraction of a second. Not a lot of data on them, so we could probably argue some of their properties, but approximately 93 are metals. Those to the left of the staircase, and including aluminum, but excluding hydrogen. Metals include group 1A, lithium through francium, all of group 2A metals, the heavier elements of group 3A starting at aluminum and down, and then group 4A, tin and lead, and then group 5A, bismuth. And in addition, the D block elements, the transition metals, and the inner transition metals, lanthanides and actinides, the F block elements, they're all metals. And metals possess to varying degrees the following physical properties. They have high electrical conductivity. Silver has the highest electrical conductivity of the elements. Copper is a second place. Mercury, the only liquid metal at room temperature, is one of the poorest metal conductors, but still conducts electricity and finds applications as a liquid electrical switch, a subject of a later course in the program. And then metals have high thermal conductivity. Among the solids, metals are by far the best conductors of heat. Here's a couple photos to illustrate. Metals serve as electrical conductors and thermal conductors. Metals have characteristic luster. Many of them, most of them, are silvery white in appearance when they're polished, and that would indicate that light of all wavelengths is being reflected. You can of course think of two exceptions, gold and copper. They absorb some light in the blue region of the spectrum, and hence they appear yellow and orange respectively. We just looked at copper. Here's gold on the right with its characteristic color, and this is the 9-meter diameter nickel statue made of nickel in Sudbury, characteristically silvery white in appearance. Metals are flexible. The terms we use are ductile and malleable. You should know the difference between them. Malleable means able to be shaped by hammering, typically when hot. Metals have that ability. Ductile means capable of being drawn into a wire. These are important physical properties of metals. And lastly, the metals are all solids at room temperature, with of course the exception of mercury. Here's a picture of mercury. It's quite dense. The density is 13.6 grams per milliliter. That's 13.6 times denser than water. Page 48, physical properties of nonmetals. "18 of the 118 elements are nonmetals. They lie to the right of the staircase. They're the ones colored orange on this table, except for hydrogen, which is also a nonmetal and is on the far left. Nonmetals have few metallic properties. Except for selenium, or the graphite form of carbon, nonmetals are non-conductors of electricity. They are electrical insulators. Take a look at these pictures. On the far left I have a non-metallic insulator insulating a metallic conductor. This is the graphite form of carbon, and it is the exception to the rule. Graphite is a good conductor of electricity, and in fact they're used in motors. They make electrical contact with the spinning copper commutator of a motor. In older days, they were made of brushes of copper wire that would drag on the commutator, but they've been replaced by graphite, and hence they retain the name brushes. The graphite is soft. It won't scratch the copper, but it does wear out over time, and these graphite brushes need to be replaced eventually, or the motor stops working. Except for the diamond form of carbon, nonmetals are non-conductors of heat. That is, they are thermal insulators. I think we're quite familiar with insulation. We use polyurethane, we use styrofoam, which is polystyrene, we use glass, and they're all thermal insulators. Crystals of nonmetals usually have a dull rather than a shiny appearance. Solid nonmetals are brittle. They do not bend if drawn out or hammered. Instead, they shatter. Of the nonmetals, group 8A, the noble gases are unique. They exist as monatomic gases, that is, singular atoms that show no tendency to combine with other atoms of the same kind or any other kind. The other nonmetals form polyatomic molecules. You no doubt are aware of the 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And the other nonmetals are still polyatomic, like phosphorus and sulfur and selenium. Of the 18 nonmetals, 11 are gases, 6 are solids: carbon, phosphorus, sulfur, selenium, iodine, and octium, which is now called oganesson. And then bromine is a liquid. It's a corrosive, fuming liquid. Has much the same chemical properties as chlorine. It smells about the same. It has been used as a germicide in swimming pools in the same way that chlorine has. Let's skip ahead to page 50. So, the physical properties of metalloids, also called semimetals. With the exception of aluminum, all the elements touching 2 sides of the staircase on the periodic table are metalloids. That would be boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Metalloids have properties between those of metals and nonmetals. They're all solids. They look like metals. They have a lot of metallic luster. The flexibility varies. Some are flexible, some are brittle. And metalloids typically are electrical semiconductors. Silicon and germanium are the most important as semiconductors in transistors and CPUs. Take a look at this plot. You see that the electrical conductivity of metals decreases as the temperature increases. However, for metalloids, electrical conductivity actually increases as temperature increases. Please turn to page 52. Let's look at some trends in the periodic table. Now, trends in the periodic table are referred to as periodicity. We'll start with size. Size of the atoms. So these values are the radius of various atoms. The smallest being helium at approximately 31 picometers, the largest being francium at about 270 picometers. Now, different texts will quote somewhat different numbers, which speaks to the difficulty in accurately measuring the size of an atom because they're just so very small. In fact, all atoms are smaller than the wavelength of visible light, which is between 400 and 800 nanometers, and hence all atoms are invisible to visible light. So even the most powerful optical microscope could not resolve an image of an atom. To do that, we would need X-rays. X-rays with a wavelength of less than 1 picometer can be used to obtain photographic images of atoms. Take a look at the trend in size. You can see that as we move down each vertical column or family, the size increases, and I guess that makes sense because we're adding more protons and more electrons as we move down a vertical column. But what about going left to right across each period? Notice the size is decreasing, and yet we're still adding more protons and more electrons moving left to right. Doesn't that seem odd? I wonder why that is. Take a look at the next page, please. On page 53, we have some simple models of the atoms in the second period, lithium through neon, and sodium below lithium in group 1A. So lithium, atomic number 3, has 3 protons in the nucleus and 3 electrons, but it has 2 electrons in the first shell and 1 in the second shell. So the question is, what's the attractive force felt by the outermost electron? Well, it's the attractive force of the nucleus. So 3 protons exert an attractive force on the outer electron, but there are 2 electrons in the inner shell that are, at least in our model, are circling and in effect shielding or somewhat blocking the attractive force of the nucleus on the outermost electron. And so we would say the effective force of attraction, or effective nuclear charge, would be actually +3 -2 or +1. This is called the effective nuclear charge, or net core charge. The core of an atom is its protons plus any inner electrons, excluding only the valence shell electrons. So the core would be 3 protons and 2 electrons. So the net core charge for this lithium atom is actually +1, +3 -2. And the size of lithium is approximately 134 picometers. But look at beryllium. It's got 4 protons in the nucleus and 2 inner electrons that are shielding that attractive force. So the outer electrons actually feel a net core charge, or effective nuclear charge, of +2. 4 -2 is +2. That's double the attractive force, and so it makes sense that the radius of beryllium is smaller than that of lithium. The outer electrons are being pulled in tighter. Take a look at boron. 5 protons, 2 inner electrons. The effective nuclear charge will be 5 -2 is +3, and so boron is understandably smaller still. And so that same trend is seen all the way across the period. Increasing the number of protons does increase the effective nuclear charge, 4, 5, 6, 7, and by the time we get to neon, 10 protons, 2 inner electrons. The effective nuclear charge is +8, and it's the smallest in the horizontal row. What about sodium? Sodium has 11 protons, and it has 2 electrons in the first shell, 8 in the second, and then it has the 11th electron in the third shell. So the valence shell is now the third shell. And so for this 11th electron, what is the effective nuclear charge? It would be 11 -10 or +1. So the effective nuclear charge felt by the outermost electron in sodium is the same as it was in lithium, but that 11th electron is farther from the nucleus. It's in the third shell rather than the second shell, and therefore sodium is bigger. So we have a model that explains the size of the atoms. Well, how exciting is that? Well, maybe not that exciting, but it's useful. Let's go further with it. We can talk about ionization energy. Ionization energy is the energy required to ionize an atom. So, for example, lithium, when it ionizes, loses an electron and forms a lithium cation. And the energy required to remove the first electron is called the first ionization energy. So even reactive metals, like the alkali metals, this still requires energy to remove electrons from them. There is a force of attraction from the nucleus. It's just a lot less than for the nonmetals. Take a look at the ionization energies listed here in this row. For lithium, it's 520 kilojoules per mole. We go to beryllium, it's quite a bit higher. It's almost 900 kilojoules per mole. We can understand that because we can say the effective nuclear charge on the outermost electrons in beryllium is pretty much double what it is in lithium. So this pattern continues. Now there are the odd occasional little deviation, for example of boron, we'll talk about that later, but clearly as we move from left to right, we see a dramatic increase in the ionization energy, the energy required to remove an electron from the outermost shell. By the time we get to neon, it's 2100 kilojoules per mole. Very difficult to remove an electron from neon. And for sodium, notice the ionization energy, 496 kilojoules per mole, is somewhat less than that for lithium, and that we can rationalize by saying that they both have the same effective nuclear charge, but sodium's valence electron is simply farther from the nucleus, and the farther objects are separated, the weaker will be the force of attraction between them. So we can rationalize ionization energy with our simple model. Another thing we can look at is electronegativity. We'll discuss electronegativity in more detail later in this chapter, but for now let me say that electronegativity is a measure of the force of attraction that an atom holds on its outermost electrons in bonds. The force of attraction on the outermost electrons would be small in the case of an alkali metal, where the effective nuclear charge is small, and the force of attraction by the nucleus on the outermost electrons would be large in the case of a nonmetal with a high net core charge. So electronegativity follows a trend that can be rationalized using our simple model of the atom. Let's briefly revisit page 52. So we write here, so the shielding effect of the inner core electrons remains the same across each period. We still have the same number of electrons on the inner shell across each period, but the nuclear charge is increasing because there's more protons, and hence the net core charge will increase across the periods, and this decreases the atomic radii. Net core charge is often referred to as effective nuclear charge. Page 54, please. Here I've plotted the atomic radius of the elements versus the atomic number. And the trends in size are quite obvious. We can see that in going from left to right across the first period, the second period, the third period, the fourth period, there's a dramatic decrease in size. But as we move from the first period to the second period, or second to third, and so on, there's a dramatic increase in size. And we were reasonably well able to explain this in terms of net core charge or effective nuclear charge. Down below I've plotted the first ionization energy as a function of atomic number. I want to see both of these at the same time. You can see again dramatic changes moving left to right across each period, but it's exactly opposite of what we see of atomic radius. So as the radius decreases, for example in the second period, the ionization energy increases dramatically. Page 55, please. Let's look at the ionization energy a little more closely. Look across the second period. We find that after beryllium, boron takes a little drop in ionization energy. Carbon, nitrogen, and then oxygen takes a drop. So in group 3A and 6A there's a bit of a drop, and we see that again in the third period, and it occurs in the fourth, and so on. I wonder what's going on there. Let's see if we can rationalize this in terms of our model for electron filling. So groups 3A, boron, aluminum, gallium, indium, and thallium are exceptions to the general horizontal trends, right? It's going down instead of up. Take a look at their electron configurations. With boron, that fifth electron is in the 2px orbital. In the case of beryllium, its 2p orbitals are empty and the 2s orbital is full. So when ionization occurs, it's the electron from the 2px orbital that's being lost in the case of boron, but in the case of beryllium, it's an electron from the full 2s orbital that's being lost. Their ionization energies are lower than those of group 2A because 3A elements like here, have only a single electron in their outermost p orbital, and less energy is required to remove a single p orbital electron than a second s orbital electron from the same shell, because, so what's the reason? Well, the ns orbital here is lower in energy, closer to the nucleus, so these electrons are more strongly held. They're lower in energy than the np orbital, which is up here. Seems to work. All right, let's take a look at this dip that occurs from group 5 to group 6. So group 6A elements, oxygen, sulfur, selenium, tellurium, polonium, like the 3A elements, are exceptions to the horizontal trend. They have slightly lower ionization energy than the group 5A elements in the same periods. And this tells us that less energy must be required to remove, well, let's look at it. In the case of oxygen, you're removing one of the paired electrons in the 2p orbital. In the case of nitrogen, you're removing one of the singly occupied p orbital electrons. So it tells us that less energy is required to remove a paired electron from a 6A element, here it is, than to remove an unpaired p electron from a 5A element. Why would that be? Well, how about this? Removal of one electron from the 6A elements gives a half-filled set of p orbitals. These will be half-filled. And recall that half-filled and completely filled orbitals seem to have a special stability as far as the atoms are concerned. Do you recall when we looked at the electron filling of the transition metals, the first series? We saw something similar occurring. In going from vanadium to chromium, we would expect that chromium would have the electron configuration 4s2 3d4, but instead it's 4s1 3d5. So chromium promoted one of its 4s electrons to half-fill the d orbital, wound up with a half-filled set of d's and a half-filled s. And for some reason, that's more stable than having a filled s orbital and a set of d's that are neither filled nor half-filled. Now, they're probably very close in energy, but nonetheless, it seems real. In the case of copper, in going from nickel to copper, we would expect copper to have 4s2 3d9 electron configuration, but instead it winds up with 4s1 3d10. So copper promoted an electron from its 4s orbital to fill the 3ds and wound up with a set of full 3ds and half-filled s. And apparently, as far as copper is concerned, that's more stable than having a filled 4s orbital and a set of 3ds that would be neither filled nor half-filled. So again, we're just testing our model to see how it explains some of the observations we see, and it's got some credibility perhaps. Page 56, please. Electronegativity. It's a simple but very useful tool in chemistry. It's the force of attraction for bonded electrons that an atom exerts. Linus Pauling, and here he is on the right-hand side. Linus Pauling assigned numeric values to electronegativities of all the elements based on how strongly they hold electrons, with of course the exception of the noble gases because they form very few stable compounds. Nonmetals like oxygen have high electronegativity values because they attract and hold electrons strongly, often taking electrons from other elements to form an anion. For example, O plus 2 electrons forms oxide. Fluorine is the most electronegative element on the table, 4.0, and francium at 0.8 is the least electronegative element on the table. Here's another 3D illustration, complements of P interest. In general, both ionization energies and electronegativities are lowest for the elements in the far left bottom corner of the periodic table, and they are highest for elements in the top right corner of the periodic table. And these trends in electronegativity can be understood by considering that trends in atomic size and the net core charge, or what we call the effective nuclear charge. Recall that small atoms have a high net core charge or effective nuclear charge, and they exert strong attraction on bonded electrons, creating high electronegativity values. Page 57, please. Have you heard of the inert pair effect? Take a look at this. Here are the oxidation numbers of some of the p block elements. Group 3A, boron is always 3, aluminum is always 3, gallium is always 3, indium and thallium also plus 3, but also plus 1. Alright, take a look at 4A. Silicon's always 4, germanium's always 4. Tin and lead are 4, but also 2 and 4. Take a look at group 5A. Move down to the bottom. We see 5 and 3, 5 and 3, 5 and 3. So what you want to notice here is that we see in the lower part of the table the appearance of oxidation states that are 2 less than the group number. The group number is 3, so we have an oxidation state of 3 and 2 less is 1. Group number is 4, oxidation state 4 and 2 less is 2. Group number is 5, oxidation state 5 and 3. So what's going on here? Let me read this first. The tendency to form ions 2 units lower in charge than expected from the group number is called the inert pair effect. So we often are not surprised to see compounds like tin 2 oxide and tin 4 oxide, lead 2 oxide, lead 4 oxide, and such. The inert pair effect is due in part to the different energies of the valence p and the valence s electrons. Here's the valence shell p and the valence shell s electrons. They have different energies. In the later periods, valence p electrons are relatively high in energy because of the shielding, that is the reduced nuclear attraction, the reduced effective nuclear charge, provided by the n-1d electrons that are shielding the outer p electrons. So the s, and then the d, and then the p. So the p electrons are more readily removed than the s electrons from the same shell. So again, our model and electron configuration allows us to predict some of the behaviors quite well. Are you familiar with diagonal relationships in the periodic table? There are some. Lithium and magnesium are chemically similar. Both react directly with nitrogen to form nitrides. Beryllium and aluminum are chemically similar. Both are amphoteric. They react with acids and bases. And then the metalloids, boron all the way down to astatine, well, they're all metalloids on this diagonal. So these diagonal similarities, they do make some sense if we recall that metallic properties increase down each group, but then they decrease, going from left to right, or increase right to left. And so if we pick a diagonal pattern moving down, which increases metallic properties, but to the right, that lowers it, we can find a zone or a stretch here where they stay roughly the same. By moving diagonally down and to the right, we encounter chemical similarities. I wonder what the EN values are along these diagonal lines. Let's take a look. Lithium and magnesium, close. Beryllium and aluminum, very close. How about the metalloids? 2, 1.8, 1.9, 2.1, 1.9, 2.1, 1.9, 2.1, very constant. Elements of similar chemical properties lie on a diagonal line moving down and to the right. Page 58, please. Using the periodic table, we can often correctly predict the formulas of compounds based on known formulas of analogous compounds containing elements in the same groups. For example, if you know the formula of magnesium chloride, you're not surprised to find that the formulas of the other alkaline earth chlorides would be similar. BeCl2, CaCl2, SrCl2, BaCl2, and so on, right? Pretty obvious. Given the formulas of sodium chlorate, barium chromate, sodium phosphate, predict the formulas of potassium arsenate, sodium tungstate, rubidium bromate, sodium molybdate. You say, I never heard of most of those. Well, let's take a look at the table. Here I've got barium chromate. Okay? Now chromium is in group 6b, and from this formula I can tell the charge is -2 because barium's +2. What would be the formula for sodium molybdate? Well, molybdate, it's right below chromium. It's in the same family, group 6b. So my bet would be that molybdate would be MoO4 -2. And if there's sodium molybdate, there would be 2 sodiums. And that would be the correct formula for sodium molybdate. It's analogous to barium chromate. What about strontium tungstate? Well, let's find tungsten. Tungsten is right below molybdenum, also in group 6b. So I'm going to bet that the formula for tungstate would be like molybdate or chromate. It would be WO4 -2. And since it's strontium, it would be SrWO4. This doesn't work all the time, but it works a lot of the time, so it's kind of like free information. Here's sodium phosphate you're given. What's the formula for potassium arsenate? Well, you say, I never heard of potassium arsenate, but check it out in the periodic table. Phosphorus is in group 5A. Where is phosphorus? Here it is, group 5A. Arsenic's right below it, so it probably forms analogous polyatomic anions. So phosphate is PO4 -3. Why wouldn't arsenate be AsO4 -3? And you'd be right most of the time. If we want potassium, that would be K3AsO4. And perhaps a simplistic example up here. We gave you sodium chlorate. What's the formula for rubidium bromate? Well, you probably should know chlorate and bromate anyway from your study of the oxyacids and their salts, but bromate is in the same group as chlorate, and so I'd expect it's BrO3, and the charge should be -1, so rubidium bromate would look like that. What about the acid-base behavior of the element oxides? The acidity of the element oxides increases up each group, more and more acidic as we move up each group, and increases left to right across each period. So the strongest acids are the element oxides in the top right corner. Basicity of the element oxides increases down each group and right to left across each period. So the most basic element oxides are in the lower left of the table. In general, metal oxides are basic. When you put them in water, they dissolve, producing hydroxides. So sodium oxide produces sodium hydroxide. Calcium oxide produces calcium hydroxide. What about the non-metal oxides? Well, they typically are either acidic or neutral. Sometimes they're neutral. For example, the oxide of hydrogen is quite neutral. But here's some that are acidic. Carbon dioxide in water produces carbonic acid. Sulfur trioxide in water produces sulfuric acid. And then the oxides of the intermediate elements, metalloids for example, typically are amphoteric. They can dissolve in acid or base. We'll look at more detail in this coming up soon. Page 59. Trends in acidity of oxyacids. So what's an oxyacid? Well, an oxyacid, for example, sulfuric acid, contains, in addition to a non-metal, both hydrogen and oxygen. And since they contain 3 different types of atoms, oxyacids are sometimes called ternary acids. Ternary means 3 parts. And the trends in acidity of oxyacids follows the same pattern as seen in the trend of the acidity of non-metal oxides. That is, acidity increases up each group for the oxyacids and left to right across each period. Now the numbers I have in this table are called pKa values. If you haven't taken it yet, you will be this semester, but let's look briefly at that. Here I've listed the pKa values of some common acids and the pKb values of some common bases, and this gives an indication of the strength of an acid or a base. Which one do you suppose is stronger as an acid, water or hydrogen chloride or sulfuric acid? Well, yes, the acids are stronger. So the lower the pKa the stronger is the acid. So it's much like pHs. These values are logarithmic values. So in going, say, from hydrofluoric acid with a pKa of 3.2 to phosphoric acid with a pKa of 2.1, it's about 1 unit difference approximately. We're saying that phosphoric acid is about 1 power of 10 times stronger than hydrofluoric, or 10 times stronger. These are powers of 10 different. Quite a range. In the case of pKbs, it's the same thing. As we move down, stronger bases have lower pKbs. Look at hydroxide is a strong base, and look at sodium hydride, a lot stronger. That's almost 10 to the 20 times stronger as a base than is hydroxide ion. Be careful with it. Let's look at our table. Notice the pKa's are decreasing left to right rather dramatically across each period. The strongest oxyacids live up in this region. Pretty consistent, and this is basically free information. You've learned one trend, and now from that you can get 4 more trends out of it for free. It's a great deal. Page 60. How about the acidity and basicity of the elements? Can an element be an acid or a base? Wow, is that true? Well, turns out that most metals are reducing agents and basic. They reduce water to produce hydrogen gas and hydroxide. So even less active metals like iron will produce base in aqueous solution. You might have to heat this up a bit, but it still does. So iron will reduce steam, producing ferric ion and hydroxide ion. Now some metals are exceptions. For example, copper, silver, gold, mercury, palladium, platinum. They will not reduce water and nor produce hydroxide, so they must be considered inert and neutral. And aluminum is amphoteric, as we'll see in an upcoming lab. The metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. They are neutral. They're amphoteric. Beryllium is also neutral in water. How about nonmetals? Well, some are oxidizing. Now some do not react with water and must be considered neutral, like hydrogen, oxygen, nitrogen, phosphorus, sulfur. They will not affect the pH of water. But the nonmetals that react with water produce aqueous acids. For example, fluorine reacts with water to produce hydrogen fluoride. Chlorine reacts with water to produce hydrochloric and hypochlorous acid. In this table, the numeric values are Linus Pauling's electronegativity values. In the table, the metals, which are to the left of the staircase, that are basic, are shaded gray. Nonmetals to the right of the staircase that are acidic are also shaded gray, and the elements that are not shaded are neutral. And this is probably a good place to stop for this lesson. We have one final lesson dealing with the acidity and basicity of the element oxides and the hydrides.